epic. So for the question, how do we know if a matching is stable? And there are a few ways to figure out that a matching is stable. One is to say this matching is a result of an algorithm that I know that produces only stable matchings. For example, the result of the TMA. That's the one algorithm that we covered in class. And that's, I'll consider it the easiest way. Because if you can say there is, I can run the TMA and that's a matching that I'll get for sure, then you know, and we proved the TMA produces stable matchings, well, then we are good. But then there is no doubt, whatever we get is a stable matching. That's the easy way. The harder way is to say I want to prove that there is no wrong couple. That is, for every couple not married to each other, I look at them, I look what is the ranking of the ones they are married to, the spouses, what is the ranking of these pairs that we are just looking at, which is not married to each other, and ask, is this pair is a wrong couple or not? That's more of a headache. And as a hint in one of the questions of the homeworks, you can solve this question in either way, but I think that one is easier for the other, and the first is in general much easier. Something is, well, this machine seems to be unhappy. What does it do? Do you think that Zoom will close? Yeah, mysteries of Zoom. Yeah, and tomorrow we'll play a bit with active learning. We've seen active learning before, if not, then I'll divide it into groups, as many as it makes sense in this classroom. Plus, whoever I'll convince to join us via Zoom. I expect everybody to join us via Zoom, but I don't know. But I also know some people are working, so maybe we'll insist that everybody today, unless we have absolutely justified reason, will join us, and we'll solve a few problems related to the homework, related to the material, and so on. What did we cover yesterday? We fully covered what's the definition of pessimality, what's the definition of optimality in stable matching, and we showed the difference between the top choice versus the optimal choice and the bottom choice versus the pessimal choice. These are usually not the same things. And then we talked about a merge sort, and as I said, another hint for the homework, merge sort has many problems that doesn't look like merge sort to start with, but you can think about them using the same idea of maybe if I handle something like sorting and think about how do I sort pairs, and then think how do I take pairs that are sorted and make them into 4 tuples, merge pairs into 4 tuples, merge 4 tuples. It's there are plenty of other problems, some that you get in the homework and midterm or midterm, that I can ask that are not about sorting directly, but definitely the same principles of divide and conquer, or either you're via quick sort or via merge sort together with the analysis will help you. Another hint for the homework. And I thought that today I will talk about a skip list, and I know some of you have covered it in 345 probably, so maybe I'll get to pieces that will be a bit, I hope that there will be new things about it, but I didn't check in details what is what. More insight, because it's actually SkipList, again, I love it because besides its coolness, I love it because there are a lot of principles that we can take from SkipList and transform to other algorithms, and are very, very deep and useful. Okay, so I want to talk about SkipList, and I wanted to speak before SkipList just to speak about linked list. Linked list is set of cells in memory, and each cell has a key. Sometimes a key comes with a pointer or some auxiliary data. Like if you think that the key is a student ID, the auxiliary data, satellite data, is maybe the student name, the student address, the student's grade. These are all the auxiliary data that comes with a key, which might be just the student ID, and a pointer to the next cell in this list. Pointer going as an arrow. If you are familiar with C, you know pointer very well. If it was a while since you looked at C, think about the pointer as the address in memory of the next cell. And as we see, the address might be actually address in memory or address in other medias of storage. Address in a disk is just fine. Right. What is an address? Where in the memory the next cell is? Or it could be just that I keep all my elements in an array, and every cell, so for this lousy color contrast, it looks better on my screen. That every cell has where the cell is in memory, 102, 4, 6, 8. Let's just assuming that your memory consists of 2 words, maybe every element in memory, and every cell we use 1 word to store the key and 1 word to store the next, and the next here is nothing but an index of the array, of the address in the array of the next cell. So saying that B is an array to C, implying that the cell of B will store as the next one, that the next cell, to find where the next cell is, go to memory address 118, because that's what the cell told me, the next of B, and that's where cell C is living. But that's one directional linked list. In a linked list, we also store 1 variable in addition, called the head, that tells us where in memory is the first element in the list. The reason that I'm mentioning all of it, because building toward the skip list. But we first visiting just normal linked lists. Sure. That's singly connected, and what can we do about it? We can start from the head and performing the loop that will visit all the elements. And we need some decision about what is a null pointer. We can decide that null, D, here we store for the address 0 is not legal address. So I'll use it to indicate null. I point to nobody. There is no next cell, so I am the last one. Makes sense? By the way, I also use this example to show you that the cells don't have to be contiguous in the way that they are installed in memory, right? The A is stored here, D stores to its left, B stores to its right, completely random axis. Okay, I can speak about doubly connected linked list. where I have both pointers from each cell to the previous element and pointers to the next element. Both pointers to the left and to the right. So show me an element, I can move to the left and I can move to the right. And the last one, the next of the last one points to next. In the first element, the previous pointer, prev, points to null. Why will I want to keep a list in other doubly connected rather than singly connected? It's because it's a bit easier to delete elements from this list. If you just show me an element, I can delete it by just find its neighbors and make them points to each other. And it's easier also to insert elements to this list. Now let's assume that I keep the list, the keys in the list, I'll keep them in a sorted way. And make my life easier by keeping the keys in a sorted way. Key 7 is smaller than 14, smaller than 21, yada yada. And I'll still store a pointer to the head, but I already introduced one new idea, which is to keep this essential, this infinity over here, such element. That is, how do I implement it? I use a constant like max int or max float or whatever, well-defined in your language. And why are you keeping this element over here at the end? It's not part of the data, this infinity over here. Instead, it makes all the code that you're writing much easier. Why? Because when we delete or insert an element, if we are deleting the very last element in a normal in the list that I showed earlier, the last element needs some special attention, so we need to check if are we in the case of deleting the last element, saying if we are inserting the last, and saying, so we need our code now contains many more if condition of are we in the case of the last cell, are we in the case of intermediate cell, and it's different treatment. Instead, I prefer to keep my code as simple as possible and waste tiny bit of raw memory by keeping this cell as infinity. And for the very same reason, I'll keep the first element also not part of the list as minus infinity. Okay, two extra elements just to keep them. And why do I do this whole gymnastic? Is that now if I'm searching for an element x in the list, you give me a value 17, and I'm looking for 17 in the list. What should I do? I start from the head, create a pointer that points to the head and pointing to it. And as long as P, it's notation of C, P arrow key, that is the value of the keys that the stores to, is, as long as it's smaller than x, perform P equals next to P. Move your pointer one element forward. Okay, and then I return P, and it's up to, does it mean that I have found P or that P necessarily points to the element that contains X? Yes or no? Help? It might be the element P, I return P the moment that this condition of the next, the P key, the element that P points to, arrow that P points to, is smaller than X. Meaning that I will return P when it's either an element that equals to X or element that is larger than X. But I also stop, it's whomever that called this piece of code should has a responsibility to check did I actually find X or not. But you already see how why it's easier to use these conditions. Why it's easier to have this loop when I keep the infinity over here. Because in general, if you ask in C, well, if P points to null, and you're asking what is P dot key, in normal C, you'll get a corner. Everything will crash with big noise. Why? Because you ask what is P dot key when P doesn't go points to normal elements. For example, P points to null. In this case, I'm always sure that this is not an infinite loop. And this question of what is P key is always legit. It will not create a call. Now, sometimes I don't want necessarily to return the element which is proceeding of the one x. I don't want to return the element that contains x, but I want to return the element that precedes x, one element before. I will not return the element that contains x. If I'm looking for 71, I will not return 71 over. Here I want to return a pointer to the element that comes before the 71. Sometimes. For sometimes meaning like in the next slide. So what I'll do, I'll replace this while by P next key smaller than x instead of P of key smaller than x. So again, in this loop, if I'm performing find of 40 in this loop, find of 40, what am I doing? Infinity smaller than 40, smaller than 40, smaller than 40, smaller, 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 larger than 40. That's the element that at this element I stop, at this element the while is false, and I return P. If I'm performing x equal 40, doing the same gymnastic, then my find of 40 will return this element, one element earlier. And while you will see in a moment, but as you see, no special treatment for the last element. And I don't need to check, did I reach the end of the list? No need to waste energy of checking, am I at the end of the list? Okay, now let's see how to insert 35. And that will also answer the question, why did I want an element, the element preceding x rather than the element containing x? So I'm looking to insert 35. So first I'm performing the find that you saw in the bottom of the list of 35. P points to this guy, P next key is 7, 7 smaller than 35, then P equal P next, 7 next, 14 still smaller than 35, yada yada. When P points to the 32, then P key is 32, but P next key is 37, which is larger than 35. So I stopped the while when this is P. And now you just follow the code in C. This is very old style C, even before C++. I'm using malloc. You can use new command as well. Creating a new cell animation. Create a new cell, asking for memory for a new cell, pointing by the pointer P1, place the key inside, and now I'm performing P of next, P1 of next will be the P of next, that is, I'll generate this pointer. I'll generate this pointer, and now I'll finally can change what is P of next. And that's why I needed to have the element just before. Okay, and once again, nothing in this code cares if you are inserting before or after the very last element. And in the same way, the code doesn't care if you are inserting a very new first element in the list. But code is the same. If I start when p points to the infinity and I want to insert 4, the code will be word by word the same. People, you're all very quiet, all obvious. How many of you took a C course? Or like 1, 2, 3? Okay, fine. So you didn't take no, you didn't take a C. Oh, have you studied C or C++?
Long time ago.
Okay, that's what you want to take from it is just a responsibility of you're asking for pieces of memory, and sometimes you even have to declare that they are garbage and to refresh them, as opposed to Java, etc. Do all garbage collection through it. Deleting an element from the list, same thing. I want to delete 37. Find the element preceding 37, happens to be the 32. So P points to 32, element before 37. And all I do is P of next equals P1 of next. It's just use it. The next pointer will move to point into the next of P. By doing so, I remove 37 from the list. And if I'm a good citizen in C, I will also say free, tell the operating system, I don't need this cell anymore, you can use it. Okay, we're done, I think, with sorted list. The sorting here implies that if I'm looking for 37, by the way, and I didn't find it before 37, then sorting means no reason to look for it after the 37, because it's definitely not after it. It's a sorted list. Okay. And the deletion, just as the insertion, no need for special attention for deleting the very first element or the very last element. Because the very last element is 170. It's not the infinity. The infinity always stays there. It's not part of the data. Okay, so just change these copies and release. Okay, now let's talk about SkipList. If you haven't seen SkipList, I'll first draw a lot of rules, and then all these rules will start to make sense. But when I'll list all these rules, they will sound very archaic. So, a SkipList is a data structure that maintains keys in a sorted order. And it will consist of several levels, maybe one, maybe more levels. I'll start, in my notation, level 1 is the lowermost level. Level 1 is the lowermost level. Each and every key in the data appears in level 1. Level 1 contains all the keys that you have in your data as a sorted linked list, one directional linked list, and as before with the minus infinity and infinity. So everybody is in level 1. Now, each level by itself is sorted. Looking at level 1, all the keys are sorted. Looking at level 2, all the keys, 7, 21, 37, are sorted. Same goes for level 3. Minus infinity, smaller than 21, smaller than 37, and so on. Each level is a sorted list. If a key X appeared in level I, and I, then it also appears in the levels below level I. If 21 happens to appear in level 3, then it must also appear in level 2, and it must also appear in level 1 as a level. 7 doesn't appear in level 3, does appear in level 2, then it must also appear in level 1. put this rule in different words, the elements in level I, it's important enough to write it, keys in level I set of keys in level I is a subset of keys in level I minus 1. The keys that you see in level 2, this is a subset of the keys in level 1. The keys in level 3 is a subset of the keys in level 2, which is by itself a subset of the keys in level 1. Each element in each level contains this element, the minus infinity, because every level is a sorted linked list. Each level also contains, the last element in each level is a plus infinity over here. And the very first element in the top list is stored outside by some outside variable called the top. Top points to the leftmost uppermost element. Now, if your keys have some auxiliary data, a few words. First, notice about the distinction between element or cell versus element is a cell, but an element is not a key. Element is a cell, element and cells are used indistinguishably. Element and key are different things. I have 3 cells, 3 disks over here. They all contain the very same key. A key might appear in multiple cells. That's all I'm trying to say. From each element, you have a next pointer to the next element in the very same level. Next pointer points to the next element in the very same pointer. Down pointer points to the cell with the very same key just below it. Okay, so you have these 2 pointers, these 2 references, these 2 fields that keeps addresses of memory of other cells. Yes.
Are each level separate memory allocations, like the 21 in level 2 and 21 in level 3 are separate memory? Okay.
Yes. I'll mention a version of the skip list that is arranged slightly different in memory that is better and worse, depending on which aspect you're considering. There are other ways. That's a version of the skip list that we are studying now. Okay, now all the elements at level 2, 3, 4, everything above 1 has a down pointer that points to an element, just with the very same key just below me. This 21 has a down pointer to this 21 that has a down pointer to this 21. What about this element? It also has a down pointer, but this down pointer, this address that I store as a down pointer is 0, 9. How do I know that I'm at the very bottom? I'm looking at the down pointer, but the down pointer points to null. That's how I know that I'm in the lowermost level. Okay, and I should maintain somewhere a counter that counts the number of levels. Okay, and now we can start to think about how what these levels might indicate analogies the main likes to use is that here is a slow train in Manhattan and that's the stations. The slow train will stop at Street 7, Street 14, Street 21, Street 32, all the stations around Manhattan. Right. The intermediate train will stop only on several of these stations, and the fast train will stop in even subset of these stations. And I might have more levels. Here is an empty skip list. No data elements. I highlight it because I still have the infinity and minus infinity. And I still have the top. It's not the only possible empty skip list. It might have more levels. It's an example of an empty skip list. But there could be a lot of ways, a lot of forms for the same skip. Okay, let's find an element with a key x, and as before, I want to return a pointer to the element actually preceding x. Not to x itself, but to the element just preceding x. And now we start to understand what's happening here. I can think about a skip list as something that consists of blocks, or let's start even this analogy, even first. Here is a search tree. But what about the search tree? If I have a value y at the root, then in the right subtree, I'll have all the keys x such that all the keys which are smaller or equal than y. Everybody in the right subtree, I only have keys that are larger than y. How do I use it? Why is this faster? Let's assume that I'm looking for the value 55 in this tree. I can go and check each and every element in its turn. Are you 55? Are you 55? Are you 55? But how does the structure of the search tree actually helps me is that I'm looking at the root and asking the root, are you 55? If the answer is no, then it says, you know what? You don't need to check each and every element. You can actually jump over a lot of elements as long as they are nicely clustered together. Who are the elements that you are jumping over? All the elements that if you are looking for find 55, if the root is 30, then I'm sure that everybody in the left subtree is not 55. So I can jump over them if I check things sequentially. I don't need to check each one of these guys because definitely the root has no clue if 55 is or is not. But the root is sure everybody in the left subtree is even smaller than me, which implies, though you can jump over all the possibly many elements in the right subtree. In which way the skip list tries to look at the same philosophy? Skip list thinks about a bunch of blocks of data. So there is lots of keys, 7, 14, many keys over here, many keys over here, 21. And my question is, if I'm looking for a key, can I jump over all the keys in this block and move to the next block? Maybe there is a big cluster of keys that are irrelevant for my search, and I can jump over them. Hence the word skip list. Okay, so what's the idea? I'm looking for an element, x, and I'll try to stay during my search as high as possible. I want to have as large jumps as possible. So I'll start from the very first, the very top level. And I will ask, is it safe to jump over all the keys which are between P and P dot next? Is it safe to search? I'm looking for X. Is it safe to jump to the next element in the very same level? Safe to search Y, because even when I'm looking at P and looking at the P next key, I'm always looking ahead one element. Looking ahead one element, if the next one is already smaller than X, then it's safe to jump over it. If not, then we'll have to do something else when we're looking for X. So let's say that I'm performing find of 117. I start when P points to this guy. Safe to jump, yes, 21 is smaller than 117. Safe to jump to the next one is P next key, which is 37. Still small or equals than X, yes, jump. And from 37, is it safe to jump? No. What do I mean safe to jump? It means all the keys that are in this block, all the keys which are in this block are all smaller than X in this aspect. It's safe to jump. You'll need it in some of the homeworks, this breaking up of the ideas to do. So I'm jumping over everybody in this. By going from here to here, I'm jumping over all the elements in this block. All the keys in this block. 37, the next one is not safe to jump because infinity is not smaller than X. So at this point, I'm checking if I can go down or am I already in the lowermost level. If I'm already in the lowermost level, we'll see in a second what happens. Otherwise, I'm just setting P to move to P down. Move down one element, P equal P down, and go continue with your Y. Continue in the Y1, so we are inside the inner Y. You've seen this type of code with this part, that this loop looks that it wants to infinity, but the way that we are exiting this loop comes from this command, from this return. That's why it's not really an infinite loop. Okay, from this 37, I go down one element to an element with the same key, an element with the same key that sits just below the 37. And in this level, I start this Y again, move to the right because 71 is safe. Cannot move to the right again, so needs to go down to 71. 85, next of 85 is already 107, so I stop and return this element. Remember, I'm looking for 170 and 117, but I'm returning one element that comes before the 170. And same goes also if I'm looking for 116, I'll also return this guy. Okay, so this will be our general path of the search. Sometimes the search path will have to go all the way down and continue all the way to the right. Sometimes our search will stay for a while in the same level, go down, stay for a while in the same level, and so on. Now, I'm not guaranteeing, even not in this example, that in every level we'll stay very little time. We'll only visiting one element in a level. It's not a search tree. We might visit a few levels in the same, a few keys in the same level. An excellent question is, what should I do if I'm looking for 37 and my search ends in this 37? Again, if I'm looking for 37 and I already found it in level 3, then should I return or not? And the answer here is that, and it's not in the code, the answer is that depending why are you looking for 37. If you're checking is student with ID 37 exists in the system, you can say, yes, I just found an evidence that this student exists. If you also want the details of students, the names, grades, addresses, and so on, then you usually store it only once. And usually you'll store it either in the lowermost level. You don't want concurrency issues. You don't want multiple copies. So only the lowermost level have all the meta data, the auxiliary data, or a pointer to a different places auxiliary data is stored. So in this case, you will have to go to visit all the way down. Make sense? So the answer is, do we have to go to level 1 or not, depending on what the purpose of the find. Okay, so this is a find. So far, it's not barely more complicated than what we did in a linked list. And I want to tell you about what is a perfect skip list. Now, a perfect skip list is my invention. Other people are using it, but I'm using it as a tool to teach skip lists, and actually it's very useful practically. And I'll talk more about what is it exactly, but let's see what my definition of a perfect skip list is. A list, I'll call it perfect if look at each one of the levels, say level 1, then I'll say between every 2 consecutive keys at level I, there is only 1 key at level I minus 1. Look at these 2 guys, 2 consecutive elements in level 2. There is only 1 element, which is strictly between them, exactly 1 element, between the 21 and 37, only the 37. Between 21 and 37, only the 32 is between these 2 guys. Right? And if I look at 2 consecutive keys at level at level 3, only the 37 appears between them. There are no 2 keys, there is no 0 keys. So how do I generate a perfect skip list? I can generate it from the top down, start from all the keys and see who is in the highermost level. And the subset, then you do something again, you do something again. That's a very tedious and not recommended way to create a perfect skip list. I don't want to construct it bottom up. Instead, I'm going to create it from the very bottom up. So that is to start from the lowermost level and makes my way up. So what am I going to do? I start from the lowermost level, level 1, and I'll say all the elements are in level 1. I just finished creating level, I'll just create level 1 by what? Well, it must contain all the keys, all the keys must appear here. You must have the minus infinity and infinity. The keys must be sorted. That's it, pretty much. That's what will make level 1. Make sure that the down pointers are all set to 9. Now, how do I create level 2? Let's think about how I create level 2. To create level 2, I'm going with 1 pointer on level 1, and now I'm just saying yes, no, yes, no, yes, no, yes, no. Completely rigidly, nothing randomness. I'm walking over level 1, and I decide that the first element that I encounter will be promoted, will appear in level 2. First key that I see will promote to level 2. Second key that I see will not be promoted. Promoted to level 2 will not, don't promote. Promote, don't promote, promote, don't promote. Promote, don't promote. Okay, and in this way I finished creating level 2. Every time that I promoted a key, 71 was promoted to level 2, of course I create the down pointer. Points will be 70. Next, I'm done creating level 2. I'm up to creating level 3. How do I create level 3? work on level 2 that you just built and do the same trick of promote, don't promote, promote, don't promote, promote, don't promote. And then you're moving to level 4. As long as level 3 exists, then you're using it to create level 4. And level 5 will already contain no keys with this part. Let's think what the running time of creating this, time to create this skip list. Time to create a perfect skip list. So I'll break this time. How much time did it take? Time to create level 1 would be, I'll assume that my keys are already sorted. I may be cheating here. I assume that the keys are already are given to me in a sorted way. A little G. So I just need to to place all of them in linear time in level 1. By the way, I'm talking both about the time and about the number of elements that I create. Okay, the time to create level 2 will be n half. I mean, actually, I'm working over level 1, but the amount of new keys that I generate is n half. But if I have n keys over here, then plus minus 1 that we don't mention in this course, floor and ceiling that we are freely dropping in this course, floor and ceiling. The number of keys in level 2 is half of the elements, is half a plus minus 1. No. I need to scan all the number of new keys that I create is n over 2. Let's continue. The time or number of new elements that I need to create level 3 will be n. How many new keys do I create? In level 2, I created n half new keys. So every second element from level 2 is going to level 3. So I'll have half of half. N over 4 keys. N over 4 keys in level 3. In level 4, I'll have n over 8. And in general, I'll have n over 2 to the I minus 1. N over n to the I minus 1, this will be the number of keys at level I. If you're not familiar with this quota sign, it's vertical quota. I mean, this word is just was above it. Right? Time to create level I. Okay, and now, and this is an important part to make sure that this is recorded. And yeah, you see me on the other side. And now I want to ask, how much time did they spend to create all these levels? Create level 1 by itself, find its linear time. Create level 2, linear time. Create level 3, n over half. Then it's over n over 4, n over 8, etc. So the total time would be n plus n over 2 plus n over 4 plus n over 8 plus, and then at some point you need to stop because I'm left out of elements after about log n levels. It's log n because how many times can I divide n by 2? Log to the base 2 of n many times. So I need to be accurate and stop it. But actually what I'll do is I'll stop somewhere here. N over 2 to the log something. But now, instead of stopping exactly at this point, I want to say this whole sum, I'm going to say it is smaller or equal than n plus n half plus n over 4 plus n over 8 plus dot, 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 dot. That is, now I'm adding a lot of terms to the summation. This is not equal to this. I'm adding some elements to the summation. Why? Because I'm ridiculously lazy and I want to make the calculation as easy as possible. So I added the n over log to the 2 to the log n plus 1 and n to over log to n. There is a lot of minuscule. I'm adding some elements, a lot of terms, infinitely many terms to the summation, but they are all ridiculously small. So now this becomes an infinite loop, an infinite sum. Let's look at this sum. It starts to look familiar. This is just n times 1 plus half plus 1 over 4 plus 1 over 8 plus go all the way to infinity. And this is a geometric sum you're all familiar with. In general, for geometric sum, if you're looking at alpha to the 0 plus alpha to the 1 plus alpha to the 2 plus dot, 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 if alpha is smaller than 1, then it's equal to 1 over 1 minus alpha. Like if you see whole exam questions where I'm asking, create perfect skip list, but don't use every second element, use every third element, and promote only every third one. That's a general summation. But in this case, if alpha is half, then 1 minus alpha is 1 minus half is half, 1 over half is 2. So we'll get that the whole summation is n times 2, which is order of n. Okay, so that's the time that it's only n times 2. The little error that I make here makes the calculation. It's at most, I maybe made a mistake of plus minus 1. It's neglectable comparing to the 2n below, meaning that the time to create this skip list was linear. And by the way, that's also the number of, that's also, right here, this is also, it was both the time, but also the number of cells. Both of them is 2n. Okay, by the way, this trick appears many times in this course. How we are starting from something that has lots of terms, they all say n, and then we are making it into geometric sum. And this summation of 1 plus half plus 1 over 4 plus will be our friends many times in this course. Okay. Facts of life, most skip lists in the world, when you are using them practically, are not perfect. Why are they not perfect? Because the structure is so elegant. It has exactly log 2 of n many levels. The search time, as you will discover in the homework, the search time will be exactly log n, log to the base 2 of n. It's very fast data structure, but let's now reveal, why do I do all this gymnastic about skip lists? It's a data structure that does what, after all? So when we are talking about such search data structure, there are a few properties that I want to be able to a few operations that I want to be able to perform. I want to be able to insert a key. So we had another brick. I want to be able to insert S into a set of keys, and X is a new key that is just added, a new student that is joining the university. New student that just joined the university. I want to be able to perform find of X in S, actually is X inside S, formally find of X in this set S, and I want to be able to perform deletion. Delete of it. The student just left the university. Of course, find if I have auxiliary data. If I have auxiliary data, student details and so on, maybe I want to retrieve the rest of the details. I'm going to add operations. I'm going to add more things, but if these are the three operations that I want to insert, and it's student ID, what would be your data structure if you have all this? If these are the only three operations, which data structure will serve you best? Insert, delete, and find only.
Hash table.
Hash table. If only you need to do if add, I mean, for hash you want to also assume that the keys are friendly. Keys are, for example, not float numbers, no, they don't have noise in the key themselves, but if you're sure that's a student name or that's a student ID, hash table, you cannot beat hash table. They give constant time per each operation. Okay, but what happens if I want to add, in addition to all these operations, the keys might have tiny little bit of noise, or possibly I want to perform also a range reporting. Range reporting of two values, x1 and x2, which would be report all keys which are smaller than x1 but smaller than x2 but larger than x1. All the keys that are between x1 and x2. If you want to support range reporting or similar to range reporting, I want to support range counting of x1 and x2. Range counting tell me how many students are between x1 and x2. I don't know their name, I don't care about their names, but I want to know how many there are. Here hash tables will be very poor choice, and you need some way to keep all the keys in a sorted method. But now you need a dynamic data structure. We will talk about how do I actually support the range reporting. All these operations I can always do in omega time. Omega of time is, if I want to shoot for an algorithm that runs in linear time, omega of time trivially check each and every key. That's in linear time. If I want to get a better running time, Then I'd like to use, for example, weight black trees or AVL trees that you might have seen before, 2-3 trees, B trees that we'll actually, I think, we'll discuss in the course, at least B trees. All over, but B trees are good trees. For IO more, less so. But 2-3 trees are very good. They are supporting times which is order of log n operation. N is the size of S, how many students you have in the university, for all the operations, except range reporting. Range reporting is an exception, obviously, because range reporting will run in order of log n plus k. K is, if I want to tell you the names of all the students, I don't guarantee that there are less than log n many students. So k here will be how many students do you actually report. So you'll have to find them, which will take log n, but it's a set of students, and if you want to report each one individually, then of course, the more students you report, the longer it takes, at least a constant time to print the name. But they want to perform all these operations in log n time. Next question. Which data structure will you propose if I want to support the find? And instead of delete and insert, and at the moment even we use outer range. So I want to do the find operation. And tell you, I'll give you all the keys ahead of time. It's not a dynamic thing. Students don't dynamically add it to the universities every once in a while, nor do they leave. Here's a big bunch of students that just arriving. You have time to sort all of them. What will be your preferred data structure now? The best data structure to support find and actually also counting and weighting. But we said hash, if you don't know hash, or you want to support counting, to support also range counting and range reporting, what would you do?
You just use an array.
You cannot beat an array. Sorted array means you are, which is, what's the name of them in JavaScript? They are ranged array, the ones that you allocate ahead of time. Ranged arrays in C, once you're asking for an array as opposed to Java, you are saying, I need 5 megabytes, gigabytes of memory, and I insist that it will be consecutive. One piece of memory ahead of time. And this will be an array, static array. Static array. Amir, help me. What am I looking for in JavaScript? The type of array that you declare its size ahead of time.
Malloc.
Was it range array?
Malloc.
Malloc is a command in C. It's not just an array, it was a...
You can define like float array, something like that.
It's, okay. Not a, I think that it was a typed array, ranged array. You are declaring what the size of each cell. You are declaring what the size of each cell. You are declaring how many cells you are going to have. It cannot be undefined. And that is as efficient as you can get. And it's as efficient as you can get for many reasons. First, you'll keep, to do the find, just keep the keys sorted. Keep the keys in a sorted way. What will be your search time? Your search time will be order log n, but that's not a big deal because all our other data structures will see also support order of log n. It will be log to the base 2 of n, which is not hard to see that this is as good as you can get. In terms of constant, that's really the minimum number of times that you'll visit it when you're doing binary search. You can choose that it's at least log n because it cannot be less, but in the worst case, it is as efficient And it's great not only for algorithms, but it's also great for debugging or optimizing. There's a compiler that works in the background and see, hey, there is a big chunk of arrays that I'll either take as a whole and sell and save to the disk or to the RDM, or bring all of it. It's very good for pieces of code that tries to validate the correctness of your program. It's very good for parallelization, handling with others. In short, if you can get static arrays, it is the fastest, it's the most important contribution to your data structure, to the performance of your algorithms. What's a bad side with sorted arrays is that if I want to insert a key, if I want to delete a key from the sorted array, maybe I can just mark it as deleted. That is somehow okay. So I did not mention SSD. When you work with SSD like to take a big block of memory, much more than I said, and either read all of them or write the whole block. Hard drive much more than this. It's great if you can, in one I/O operation of one bringing of piece of memory in and out, you can get all the elements of an array all at once. Deleting start to be ugly. I need to write somewhere here maybe, but I still can get away. If I want to insert a new element and keep the array sorted, then it will not work. The only way to insert a new element into a sorted array will be to shift each and every element to the side. You need to shift n elements to the side just to make room for one new element. So all the advantage of sorted array goes away the moment that you are that you want to insert new keys. Perfect skip list, also not too bad. Not as good as sorted array, but also not too bad. But again, I don't know how to add elements to the perfect skip list and keep it perfect. Usually I cannot. But I will still be able to keep it as a completely legit skip list. That's going to be fine. Okay. Still, the algorithm that I described to you is not theoretically. It was also a good way for us to rehearse this whole procedure. Also to talk about the memory. Also, we are going to use it very soon about real skip list. And also, if you are having a skip list and its performances are degrading, and you have a few minutes for maintaining it, take all the keys in the skip list, all the keys in a sorted way, throw away the old skip list, and run this code that is linear time very fast. And this is as nice skip list as you can get. So it's good for maintenance of the list. Okay, here is a search operation in the skip list. And what I'll ask you to do in the homework is to prove that in a perfect skip list, you'll never spend more than you'll never visit more than 2 keys in the same level. You'll never visit more than 2 keys in the very same level. Why? Because if you're visiting 3, then one of them, if you're visiting 3, actually more than 1 plus minus infinity, if you're visiting 3, definitely one of them also participated in one level above, and you had to visit this guy from above. You would not spend all these guys over here because 71 is somewhere in the middle. That's a hint of why it's only one element from each level. Okay, search in a perfect skip list. Just example, the very same thing. I'm performing a find of 71, just an example. Once again, jump to the 71, already find it. Depending on what's the purpose, do I go all the way down or not? Either case, how many levels do I have in a perfect skip list? We talked about it, log n. Now, what will be the time for the search? It depending how much time I'm spending in each level, but if it's perfect, then I will never visit more than 1 key in each level. and I said there are only log n levels, so the overall time will be log n for the search. In the real skip list, things are going to be a bit harder. Okay, now inserting a new elements into a skip list. And here I don't assume that the skip list to start with is sorted or is perfect or not. I just want to insert a new element. Let's talk about the algorithm for insertion. Now, we know that a very nice skip list is if it is perfect. Very ugly skip list will be if all the elements are only in level 1. Notice that there is a very subtle thing about balancing here. If all the elements participate in all the levels, all the way up to level 3, then it's very poor skip list. If all of them participate in level 3. If none of them participate in level 3, it's also a very poor skip list. If they only in level 1 only. Right? Because either way, if you're performing a find and all your elements are in level 1, what you do is just go in the lower most level, spending linear time. The very same will happen if everybody's in level 3. So you need some balance of how many levels inside them. So I want to keep this way to balance thing. And when I'm inserting a new element, the first step is to determine an integer, I call it k, which will tell me in how many levels x will participate. The newcomer will participate. K, again, is a value that I'm going to show you the algorithm of how to determine. And k will tell me in how many levels the x is going to participate. Now, once I know in how many levels it's going to participate, I also know which levels they are. Because it's always, if it participates only in one level, it must be the lowermost one. Participate in 2 levels, it must be the 2 lowermost levels, and so on. If k will be 4, it will mean it participates in the 4 lowermost level, which will mean create a new level. But the first step is to determine what is k. I'm going to insert x. I want to determine what is k. Let's assume that I already determine what is k. I'm going to perform now find of x. Animation, animation. Oh, yes, there is animation. Okay, I performed find of x. But this time I remember who are the keys that I visited during the find operation. So I'm performing, in this case, find of 119, and I do my find of 119, stop at the lowermost level, but I'll keep the elements that I passed through, or to be more precise, out of all the elements that I passed through, I know as I'm going down who are the levels that the newcomer is going to participate in, and I'll keep these ones. It will be clear from when I'll continue. So I'll keep something in memory during my search. So far, it's just search, very analogous to what I did in a linked list. And if I want to insert 119, here is my path. I decided somehow, I didn't tell you yet how, I decided somehow that 119 will participate in 2 levels, k equal 2. And what do I do in each level of these 2 lowermost levels? Insert 119 exactly the same way that you did in a linked list. What you did in a sorted linked list, just do it in the lowermost level, maybe the one above it, maybe the one above it, just as you did in 119. And which, to be more precise, look at this 71. Why in this 71 did I go down and did not continue to the right? Because the next element to the right is larger than 119, implying that if 119 is going to be inserted in this level, it's going to be right after the element at which I went down. It is from a cell during the insert of 119. If from a cell I went to the right, then the cell is not affected from the insert. If, on the other hand, from a cell I went down, then 119 is going to be right after this cell that I just went down over, if it will be inserted in this level at all. Okay, so I insert 119 right after the predecessor of 119 in level 2, also in level 1, and I just make sure that the down pointer goes down. Some people prefer to do it in a top-down process, like to keep track of everything and insert X to every level as you're going down. Some people will say, I'll store this path in my recursion stack and insert it on my way up. Both ways are fine. Okay, so just insert as if it's normal skip list, and just maintain the down pointer. And now we are getting to the heart of the skip list of determining what is K. Because I want to have the skip list as close to being perfect as possible. So maybe I need balancing. Maybe I need some fancy algorithm to determine K. And before it, I want to show you how I insert 119, but this time K happens to be 4. So I'll insert 119 in each one of the 4 levels in the skip list. Which implies, by the way, since I know how many levels I keep in my skip list, it used to be 3, and now K equals 4, that's my trigger to create one new level for the 119 and insert it to this level as well. It's fine. So K might be larger than the quad number of levels, which just implies do the same as before, but generate one or more new levels. Okay, we got to the heart of it. How do I determine K? How do I determine K? How many levels K participate? And that's how it goes. You're taking a coin. You're taking, and you say, I'll start when K equals 1, meaning my new element, X, is going to participate for sure in one level. For sure, my key will participate in one level. Now, throw the coin, and if it happens to be face, then K plus plus, increment K, and go to throw the coin once again. If your coin says it's a tail, then you don't increment K, and you don't give the coin another chance. Okay, so I throw. So I start when K equals 1, I throw the coin and I got face, then I increment the coin, I increment K to 2, throw the coin again, happens to be face, increment K, 3, throw the coin, happens to be tail, and I stop at this point. So in this case, K will be small, K will be 3. So every time the K has a chance of 50% to be upgraded, and 50% chance to stop the experiment right now, this determining K. And it's absolutely ingenious because there is nothing here that says what the skip list looks like. There is nothing here that says how many keys do I have, or should it be balanced or not. It's absolutely oblivious to what happened in the skip list, how I determine K. A bit technicality, since I cannot throw coins really in my computer. When I write a code, I call it our RMD, our rand, that will return either head 0 or 1 with probability, maybe 50-50. We'll talk about other probabilities, but it will turn either 0 or 1. And now my code is just saying, start when k is 1, and now perform your experiment. If you happen to be 1, then do k plus plus and do the experiment again. Happen to be 1, do the experiment plus again, and so on. Okay, and this simple code is all I need to provide a lot of great properties. Before continuing, how do I delete an element from the skip list? I want to delete 71. Remember, I spent a lot of time at the beginning of this meeting discussing the deletion from a linked list, from a single linked list. How do I delete element from a skip list? I just find it. So normally when I find it, I find the element preceding it and the element before it in each level. And what did I do in a linked list? Say the next pointer is going to be the next pointer. That is jump over the elements over here. That is, if I look for 71, I found all the elements in this search, the 37, and I'll tell the next pointer, point to the next, to infinity, point to the next. And this one, 71, is eliminated from the linked list. Now, it might be that because of this deletion, the top list, the top level becomes empty. Then you can get rid of it. You don't have to, but you can get rid of it. Okay, and then you are decreasing the number of levels. Okay. Now, let's try to analyze how many cells I expect to find in this skip list. So, in a search tree, there are linear number of elements. But here I never limit. One key can participate in many cells. So in how many cells do I expect to find? And notice that from now on, everything is randomized. If you have a really bad karma, then every key will participate in many levels, and you've got a very non-efficient and very tall skip list.
With the randomization, do we still have a requirement that we only add one level per insert?
You could. But my code doesn't, and you'll see why. You'll see a bit later why not. We're going to go a bit through the math, and we'll see that yes, it's a randomized data structure. There is a chance it will fail. The chance that you'll be struck by lightning during this execution is much higher than the chances that the skip list will fail miserably. That's essentially where we are going and what we are going to prove. Well, the chances of failure is so small that it's fantastic data structure, and practically it's indeed satisfies what it's promised. It's really that efficient for all these operations. So let's ask with height some facts about the skip list. What is the height of the skip list? And there is a bit hand waving here, and I'll get back to a more concrete proof. But let's try to hand wave a bit. What is the chance of an element to participate in level 1? What's the probability that an element, that a key X participate in level 1? 100%. For sure it will participate. Everybody, our loop starts when k equal 1, and every element must participate in level 1. So no randomness here. So how many keys participate in level 1? All n of them. Look at each one of these levels, of these keys. Now I'm tossing the coin, and the coin has 50-50 chance to promote an element to level 2, and 50 chance that it will stay in level 1. So I have n keys. The probability of each one of them to be promoted to level 2 is half. So if half each element has a 50-50 chance, and the chance of then I expect to find half of the keys in level 2. N over 2 keys will be in level 2. That's the average number, the expected number. And it'll be more formulated. What about level 3? To compute the level 3, I can do very hairy, complicated thing and ask, hey, to make it to level 3, an element needs to, I'll try to estimate how many elements are in level 2 and try to apply something probability. I can make it more complicated or to make it much simpler by saying, for an element x, what should happen to x to make it to level 2? Maybe to level more than 2, but to level 2, what does it have to do? It needs to get a face at the first one, and need to get a face for the second one. Then it will make it to level 3, maybe to level higher, maybe not. So the chance that it will make it to level 3 will be exactly, the results of the first 2 trials can be tail-tail, tail-head, head-head, head-tail. Only one combination brings you to level 3. So the probability is 1 over 4. So the number of elements that you expect to find in this level is n over 4. Which means that the number of elements in level j is half to the power j minus 1. J minus 1 because I start to count at 1, not in 0. Okay, so what happens after log n main levels? I'm running out of keys. Okay, so that's the number of levels that I'll get will be log n. And looking at the very same sum, what is the expected number of cells that I expect to find? We talked about it when we discussed perfect skip list. Now it's not perfect, but the same math will still work. This is the expected numbers of keys in level 1. This is the expected number of keys in level 2, level 3, level 4, and so on, which is just smaller or equal than n times 1 plus half plus 1 over 8 plus 2. Okay, and a more rigorous proof for some of the arguments will require the use of random variables. Then you're getting it immediately because it's just expectation of sum is sum of expectation. If you're not familiar with this, we'll cover some of it more. However, with my very, very stupid algorithm of just tossing coins, I'm getting a data structure that has log n levels. And they will be very nicely spread, and we'll have linear memory. Linear memory are expected to be 2n. And to estimate how ingenious this data structure is, you need to really know that this data structure will support insert and delete and the other operations that we mentioned in log n time. Sure, it will be expected log n, but it will be log n. Now you can get the same time also with AVL trees, or red-black trees, or 2-3 trees, or many other balanced search trees that you have seen. But if you try to implement them, you probably spend a few days of, for example, for AVL tree, you have cases of a new element is going to the left subtree of the left subtree, or left subtree of the right subtree, or left or right, left, right, right. Tons of other cases that implies that you need to spend much more time writing it than about 5 times to debug it and maintain it. And the code itself is much slower than SkipList because there is so many ifs to check. SkipList will provide this log n only with in the expected sense. It comes with a tail estimation that will say the chance that we are failing to get the log n is exponentially small. I'll show you what I mean. Chance that I'll stay is exponentially small, but the constants that SkipList are getting, the actual performances, the actual running time when you count seconds, are much faster than almost every other search tree that you can have. If you are just because there is so much simple to check. And if you see, say, the main videos that I have a link to, Professor at MIT that said that it took 2 hours to implement it. I think that for all of you it will take maybe more than 2, but not much more. You'll all be done with this in half a day, I think. Really, what I showed you is the whole code outer. Now, there is a rule of preservation of effort. The code is very simple, very easy to write, very easy to maintain, very easy to modify. But the effort will be now to prove that things are working, understand exactly why. It will be a bit more than what we did, what you did in other search trees. So the effort will be more intellectual, but the code itself is just very simple. So as you covered it in 345, I'll try to give you a few hints of why it works. In particularly, and it's just the promo, after a few steps of playing with probabilities, you will all be able to prove that. You will ask in that promo of what we'll cover tomorrow. What is the probability that the I convince you that the height of the skip list, but I vaguely hand wave, told you something like that the height of the skip list is about log n, but order of log n. But if I want to quantify, what is the chance that it's actually larger than 7 times log to the base 2 of n? The chance that this height is more than 7 times log 2 of n, when n is only 1,000, is 1 over 10 to the 1,000. It will be the 7 that comes from here, just 7 minus 1, which is 1 over 10 to the 18. Then you're asking, hey, that still happens to be too much. What's the chance that it's higher actually than 10 times log n? Now it's larger than 1 over 10 to the 27. That is that the chance that the skip list is not too tall is larger than 1 minus this number. And that happened without me limiting that I'm just adding 1 level. That's why I said that practically it's not such a big deal going this way or another. Now, and this proof will go through tomorrow, and it's not going to be hard. It's not very really nothing complicated here, but it will take about half an hour, and then we'll solve a few questions from the related to the homework. And yeah, good. Thanks. Like it all the time.